Uh, Now, our second talk is by Mr. Zhang Wang on ideas for adding FPGA accelerators to DPDK. Zhang Wang is a software engineer at Intel and is focused on virtualization and performance optimization. And so I would like to request all the speakers to please come in front, and I would special request to Mr. Akhil Goyal, please come in front, and you can tweet about this summit at hashtag DPDK Summit. So I would like to request Mr. Xiong Wang to please come on stage and enlighten us. Thank you so much.
And then we'll talk about the partial reconfiguration and what is that. We all know that FPGA is reprogrammable, but when just like any generic computer in the early days, it's programmable, but then you can just input the program in the initialization phase, and it runs, and then it returns. That's as much as I can tell in the early days. But it's just like FPGA. So when you have more and more resources, you need better management system to manage all those resources. Not you can you can give the resource not to one user, but you can give them to multiple applications and run them at the same time and without interrupt each other. So that's the way it has to be for FPGA in the future. And also in the present, I guess it's already happening. So just take several examples, right? Why partial reconfiguration is a must in data center business. First, let's take a look. If we have FPGA acceleration for our networking, right? Like, for instance, a switch. And because why we use FPGA is because it can be reprogrammable. And just like any switch, virtual switch, we need update them, and we need to add in new features. So in that case, we don't want to shut down the whole system just to update our switch, right? And in that case, we need hard upgrade, which means we can just power on the FPGA and re-download the image, and maybe within several microseconds, the whole system will be back online again. So that's hard upgrade. And another scenario would be like infrastructure as a service. Like we can, when FPGA entering the data center, we can use it for infrastructure to be virtualized to provide service for our customers. Like, for instance, our customer said, I want 2 FPGA a month, and then I'll provide you the bitstream, and you can download them for me, and I'll just use them for 2 months. In that case, we also need partial reconfiguration. That's the statement. And then the question, let's go back to the question is, how DPDK fully support FPGA? I guess just like we have talked about is, first, we need DPDK to take care of the reprogrammable part of FPGA. And another part is we need DPDK to, just like any other device, the DPDK device model currently support, we need DPDK to take care of the actual device driver, the actual device personality of that FPGA, or it can be many devices in one FPGA, right? So now let's take a look at from hardware point of view, what we should do to support this. Just like, let's go back. I'll use a computer again to demonstrate this. So each device, you can provide many services. It has many features, but some of them are, not likely to be changed frequently, but a lot of them, like the applications, it can change over time. It can be changed very frequently. So for any system, just for like for FPGA, it's also true that if we want to do partial reconfiguration, if we want to do like how to upgrade anything like that, we need to separate those services. Like for those that like system attributes, we should make them stable and fixed just when the server boot up. So that's why, I mean, in Intel's term, there's blue, we can see the blue part and green part. So the blue part is, it's fixed when the server initialized, just like the BIOS. And the green part is actually user applications. And what the blue part does is it's still RTL, and it's still written in Verilog flag. But the only difference is it handles, it's kind of taking the management functionality. So we call it the FME, the FPGA management engine. And it has everything you need to control this personality of this FPGA. And in the middle, we can see there's another ports, right? The ports is simply the kind of like a bridge between the FME and the green part. So it's how many ports are there in this FPGA? It depends on what you do in this blue part. And then the green part is the user application, right? And we can download them. So just because we have all the PCI interface fixed in the blue B stream, so which means when we want to reprogram this green part, we don't need to shut down the whole server. We just need, you know, to just like a computer to reinstall some programs, and that's very convenient and easy. Right. Okay. I'll talk about OPE for a little bit. OPE is a software stack that for just be used for the operation we need. We have the hardware ready right now, the hardware design, and then let's go back to this page. What do we need to do to operate this FPGA is that first, it's still a PCIe device. We still need a PCIe driver to do that. And then after we find this PCIe device, we can identify there's a lot of AFUs inside of it. So we need some APIs, and so the software library and driver can provide to enumerate how many AFUs are there on this FPGA. And also we need to open them, and we need to access and manage these AFUs. So that's where OPE came into the stage. The OPE, I'll just read some of the descriptions here. OPE is a default software stack for Intel Xeon processor with both integrated and discrete FPGA devices. So this is open source, and you can go check it out on this website. Basically, it's a state of driver and libraries sit in between of the operating system and the higher level of applications and frameworks. Well, DPDK is one of them. DPDK is one of these software frameworks that OPE will be integrated into. Okay, now let's get back to the, the real business, right? FPGA acceleration on DPDK, how can we do to do that? Because currently in DPDK, we don't have any device that can support reprogrammable devices. What we do is we have scans, right? Fast scan, and we scan the driver, and then we just bend them, bend the driver with the device, and it works. But how can we support this reprogrammable device? So row device just caught our attention, which has been upstreamed in 1802. Row device, we think it's really good for FPGA, at least for now. And what we do is, our proposal is to, well, the concept is very simple, right? We use row device to take care of this PCI device of FPGA. So from that point of view, it's a PCI device, and the row device can use to control it. And then in the row device, we give them ops to do the reprogramming the FPGA. And after it's done, we will do a second scan. Well, that scan, we will have an FPGA bus, which is a global AFU list. And so when we finish the downloading of the bitstream, we will just scan it again and find out what AFU is, what the AFU device, and then we will band the DPDK device. Just like, for instance, it's an EtherDEF, right? We'll have Ether in DPDK. And OPE will be providing the common library and API for this. So, well, if you have any questions, you can interrupt me anytime, and you can also ask me questions when this is finished, right? And then I'll talk about some POC work we have done. So first model is the bare metal model, we call it, which means we dedicate this FPGA for user space usage. Just like we said in the previous page, we will have an DPDK FPGA device driver, and it will use OPE's common library, common APIs to control this FPGA. And then we can see the yellow part. It's actually the row device and the FPGA bus. And the blue part on the right-hand side, well, in the middle, is that the existing DPDK device model. If it's an Ether device, the FU is an Ether device, we can just scan it, and we will add an Ether there, right there. And of course, just like we said, OPE is a open source, and it's an library and drivers. And we don't actually need DPDK to do that. If you choose not to use DPDK, well, that's also fine. You can just call the libraries OPE directly, just like we show on the right-hand side. You can call OPE directly to do that. But it will be much, DPDK will be much easier, actually. And one thing we need to point out is that one FPGA can only be handled by one, we can call it PF driver, or in this case, the DPDK primary process, I guess. Because, you know, otherwise it will cause confusion. Who will do the reprogramming when there will be a lot of conflict. The second sample is the virtualization. And this is also very easy to understand that if we want to provide the device port, FPGA port to provide a service, we need to virtualize it. And to do that, currently we can use OPE's kernel driver to create all these VFs. And yeah, OPE will provide all of them. And then the DPDK running in the guest will be just running as usual. And you won't be aware what kind of device is there beneath. And basically that's the whole picture. And yeah, some summaries, I guess, is that first, I think the FPGA is a kind of important thing that came into DPDK, that we need the programmability and we need the performance of it. And then I think partial reconfiguration is an important requirement. It's actually a must in data center business. And then we go through the hardware readiness, the blue bitstream and green bitstream framework, and the software part, which is the OPE library, and how DPDK will do the integration of them, which we use two skins. We use row device to take control of the PCIe device, and the second scan of the FU device. Okay, that's pretty much all of my presentation. Any questions? Okay.
Your FPGA device, how you're communicating via virtual machine? I mean, it is PCI through PCI. The FPGA will be some programmable chip, right? I mean, the device, FPGA
yeah.
device,
yeah.
where you will load your program. How that will be accessed via virtualized machine?
Oh, you mean how do we access the actual FPGA, right?
Yeah.
Yeah. FPGA, we said we will use OPE to do that. And I can describe the whole process, right? First, we use row device to open this FPGA, and the driver of this row device, we integrate with OPE, which is the open programmable accelerator library, right? And that library will provide the interface to enumerate, to discover, and try to open this. It can enumerate how many FUs are there. And then it can open this device with the PCI address and AFU IDE, and you can open this FPGA like AFU, and then the port, at this time, you can access all these, like IOVA, you can get the IOVA of it, and you can map the MMIO, and then you can do the memory operation. That's basically how you interact with the FPGA. You can do MMIO.
Yeah.
Hello.
Hello. Yeah.
Kindly raise your hands so that the mic can reach you, and then you can ask the questions. Thank you so much.
Yeah. So I had a query regarding you showed ports on the FPGA. Are these faceplate ports? And um, yeah.
You mean this?
Yeah. So are those faceplate ports? And if so, as you're seeing, we are seeing the movement from 10 gig to 40 gig, and then it will go to 100 gig. So can the same FPGA be reconfigured to a higher bandwidth? And if that's the case, would that have an effect of how much compute power I can download on the FPGA? Because the FPGA is a discrete component. You can't, the number of speed transistors you have on that, that's limited. So that's the first part. The second is that is it also possible to do something of FPGA slicing, where you have some part of it doing the network function, the other part of it doing a compute intensive offload?
Yeah.
Thank you.
I'll answer the second question first. Well, you can actually, a PGA with enough resources, you can program it to do anything, right? You can program it to be any circuit. And then the first question I guess you're asking is how, I don't know if I get your questions right, but I think you're asking how do we split these resources? Is that correct? Okay. Um, the blue part, which is also written in RTL, in Verilog or any kind of language, is fixed in the beginning of the server when it's boot. So like we can say, oh, I have a lot of resources, I have a lot of transistors in this FPGA, and I can, in the blue part, we can say, well, we will support 10 or 8 ports, which means now we have like 10 bridges connecting to the green part. And then for the green part, which is the actual application, the actual resources we're going to use for our applications, right? And for that part, it's very flexible. Well, you can say I want a 1 gigabyte of memory interface for just one application, and then I will use 10 megabytes for maybe another one. It's very flexible, and yeah, basically that's I don't know if it answers your question.
Yeah. So is PCI a mandatory aspect of this integration? I'm not quite clear why PCI is even in the picture. Do I need the PCI controller to be on the FPGA? What, I mean, there are other interconnects like C6 or CAPI, and why specifically PCI?
Oh,
Yeah,
yeah, we can, for Intel's FPGA, we have PCI link and UPI link. You're talking about we have other ones, C6, others. Yeah, well, actually, this can be, this is only a framework, actually. It can be used as PCI device, but it can also, I mean, the process is actually the same, no matter what kind of, you can actually provide your own device driver to this FPGA. Not you don't have to use OPE. You can use other stuff. This is only a concept of how it works. Of course, you can replace the components with other stuff.
Any other questions? I think no. Thank you, Mr. Wang, for providing us such great insights on adding